Hi everyone, welcome to Algorithm Seminar. Today we're very happy to have Bernhard Haeupler to give a talk here. So here's his bio. He's a neurodiverse, ADHD and dyslexia, a postprof at ETH Zurich and Adjunct Professor at Carnegie Mellon University, where they were an assistant and associate professor of computer science from 2014 to 2022. They received their Ph.D. and Master of Science in Computer Science from MIT, and the Bachelor of Science and Master of Science and Diploma in Applied Mathematics from Technical University of Munich. Dr. Haeupler's research interests lie in the intersection of algorithm design, distributed and parallel computing, network optimization algorithms, and network bracket coding theory. Their research, spanning over 100 articles, was recognized with several awards, including the ACM-EATCS Doctoral Dissertation Award of Distributed Computing, the George Sprowls Dissertation Award at MIT, and various Best and Best Student Paper Awards. Their research has been funded by multiple prestigious grants, including a Sloan Research Fellowship, the NSF CAREER Award, and the ERC Award. Please welcome our speaker.
Thank you. I didn't know that this would be read, so that's embarrassing. But no, it's a great pleasure to be here. I did write in the bio that I'm neurodiverse because I think it's something that we don't talk about often enough, and it's way more common than one thinks. And so, every talk that I've given since I was free enough and safe enough to quit my job and talk openly about it, I at least spent a few minutes just acknowledging that and kind of spreading the word. So let's celebrate it. Different brains are awesome. My brain has ADHD and dyslexia, and I'm still figuring out how exactly to, I had to fit in kind of and played the game long enough and kind of had to, and now I'm free and I'm trying to figure out how to do research and how to do things my way, if I can do it completely freely. And I didn't have a lot of time to do that yet, so I'm still figuring it out. And this talk is going to be one of those where normally I would have just prepared slides. I don't have slides. Most of this will be just me talking. I'll try to draw something on the board, and please ask me, interrupt at any point of time. And also, if at some point it's helpful to draw something, tell me, and I'll try to draw something. But yeah, it's a great pleasure to be here. I want to talk about so many things, but in the end, I want to talk about kind of algorithms and the type of algorithms that I've been thinking a lot about lately is kind of graph algorithms. So we have networks, we want to compute flows, distances, clusterings, those kind of things. And I want these algorithms to be very fast. So very fast, I typically mean close to linear time. Maybe m polylog, maybe n to the 1 plus epsilon for an arbitrarily small epsilon, but significantly faster than quadratic, typically. And then there's other kind of nice properties that we would like to have from, where's the camera actually? Kind of, it's kind of here. Okay, yes, I can look at the virtual audience every now and then. So there's other nice properties that we would like to have from algorithms, which is ideally in a network, we would like things to be local. Kind of, if we compute things, it's nice if we compute things kind of whatever that means in a local level. Because maybe we're storing things locally, and this has better, cache performance. Maybe if you're doing things locally, it also has kind of advantage that if things change, we might be able to update something here and update something here, and they don't interfere. So in some sense, maybe updates can be done in a more asynchronous fashion. Also, if one does things locally, it might mean that if you're changing things here, things only change locally, which means there's kind of less, there's lower recourse. So changing the input a little bit might change the output only a little bit, which is a property that's very useful for for all kinds of things. For differential privacy, for example, this is related to sensitivity. For dynamic algorithms, this might be related to update time. For kind of synchronicity and kind of so those kind of the abstract high-level goals. I want to talk, and this is a fairly theoretical tool, but I thought it would be still kind of fun to talk about. And then maybe in a year, once I've worked more with people here, then I have more practical kind of algorithms to report on. But I want to talk a little bit about expanded decompositions and kind of an extension that we came up with over the last 2 years or something. That I think will be quite influential and kind of really powerful in extending what expanders and expanded decompositions can do. So I'll start with just saying what is an expanded decomposition, and then give you a little bit of a kind of at least a definition, a flavor of these kind of new type of expanders. And that's probably more or less how far we get in a talk like this. So expanded decomposition, I think everybody kind of knows what an expander is. I'll go over it later again. Kind of the definition is kind of any, actually, yeah, so this, actually, maybe there's a bunch of different ways to look at expanders. One is kind of they're robustly connected. Meaning that if I have a graph and I want to cut some part away from it, then the number of edges that I need to cut is proportional to the size of the piece that I want to remove from it. So this is then typically called, if the volume in here, the number of edges in here, in S, so the volume of S divided the number of edges in the cut. So if I need to cut these are K edges, if K edges over, does this work? Yeah. Over the volume or the number of edges inside here, if this ratio is at most phi for any cut S, then I call this kind of a phi expander, and that's in some sense a conductance, right? So robustness of this thing. One can also look at expanders as kind of graphs that have fast random walk mixing. So if I start a random walk at some node in the graph, and then I start running around randomly, and then the question is, when am I uniformly mixed over the whole graph? Phi can be sort of thought, at least for small phi, we get fast mixing and logarithmically in many steps, and phi in some sense measures, not exactly, but up to a square factor, kind of how far we are from rapidly mixing. There's also one way in which one can think of expanders, and this is going to be for this talk the better thing. We can think of expanders as kind of robust communication networks. Okay, in the sense that if I have an expander and I think of I want to do point-to-point communication in this network. So this node A wants to send to this node A. This node wants to send to here. Maybe the same node also wants to send a packet from here to here. And so I'm looking at these multi-commodity demands. So multi-commodity meaning there's multiple packets, and really I want this packet to arrive here, not somewhere else. And an expander, more or less, something is a phi expander. This is not really a definition, but an equivalent characterization up to some polylogs. I say something is a phi expander. If and only if any reasonable reasonable demand like this. So what means reasonable here? Well, if the graph is disconnected, then the demands that I want to send should be in the same connected component. Otherwise it's very unreasonable, right? And also maybe if we have a node here and it has kind of constant degree or small degree, and it wants to either send or receive a lot of packets, that's not reasonable, right? So reasonable here in an undirected graph could just mean kind of unit or send at most, send/receive at most. Let's say at most kind of capacity or the degree of the many packets, and within the same component. Connected component. Right. So if any reasonable demand can be routed with congestion 1/5, roughly, then a graph is a phi expander. Right. So what do we mean with congestion? So I need to find a path from here to here in the graph that routes this packet here. Right, I need to a path that sends B from here to here, something that sends C from here to here. So it could be, something like this. And the congestion, if you have no capacities, it's just the number of times that an edge is used. Right, this all generalizes to to capacities as well. Right, this is exactly. This is not really how we define expanders, but this is an equivalent definition of expanders up to a logarithmic factor, flow cut gap factor. Right. Good. So these are expanders, and these have really kind of let me maybe go to. So these are kind of tightly knit communities, clusters that are well connected among each other, right? Well connected in the sense that random walk, like are mixing, so robustly connected. They're like very good communication structures. Right? Good. Now, expanded decompositions. Yeah, so still works. It's really saying that any graph, I can look at it as a bunch of expanders plus a few extra edges. Okay. So for every G and every phi, there exists a subset of edges C, which I call the cut, a subset of F, such that G minus C. So if I remove or cut these edges in G, then is okay. So here a union of or just a phi expander. So here's somewhat, so classically we would say the union of two expanders is not an expander. It's just the union of expanders. If one uses this definition, which is kind of, I feel like in many ways actually extends much nicer, then as long as we forbid unreasonable demands, the union of two expanders is, in my language, actually is an expander, because any reasonable demand can be routed nicely. Demands that go between disconnected components are not reasonable, right? So this is really saying that for any G and phi, we can find a bunch of edges such that it is kind of an expander or union of expanders. And the important thing is that we don't need too many edges that we delete, right? So the size of C is smaller than phi times only a phi fraction, actually phi log n. Fraction of all edges. Does that statement kind of make sense? So any graph, I think of it as a friendship graph, right? A social network. I can, what are kind of expanders? Any like family, right? Where members of this family, there's an easy way to communicate. We are tightly knit structures, they're well connected, right? You cannot easily cut out a large part of the family and separate since they don't have any sparse cuts. This is saying that you can look at any social network and delete only a phi fraction of edges. So let's say a phi log n fraction. So that, for example, phi to be like 1 over log n, and you're cutting like a small constant fraction of all edges. And the remaining components are actually nice families, the vulnerable lock-in expanders. Right? Good. And so here's kind of so what are these expanded decompositions used for? They have many algorithmic uses. Say initially this whole framework, I would say, came from Spearman-Tang, which wanted to solve flow problems, multi-commodity flow problems fast. And then it turns out that basically expanders, we can do algorithms really nice and fast. And thinking of kind of putting expanders onto our graph where they belong is a good preconditioning, right? And numerically makes the whole graph much nicer, right? You can design very fast spectral algorithms, very fast kind of combinatorial algorithms for a lot of problems based on these expanded decompositions. And I want to say over the last 5 years, maybe 10 years, these things have really kind of been rediscovered and put to use on a whole host of combinatorial problems. Renato, you have a... No. Okay, cool. Yeah. Have been put to use on a host, like really large number of cut problems, flow problems, many different kinds of problems that we care about, one can solve using these expanded decompositions. And here's maybe just one kind of nice way of applying this also recursively and hierarchically. Let's do the following. I take the graph, I remove a few edges, and I get, let's see, it's too bad since we only have one board. Okay, I'll try to do this here. Kind of hierarchical expanded decomposition. So the very first thing that we could do is look at your social network, delete a small fraction of the edges, and you have these kind of tightly knit components, which are expanders, which you should think of your families, right? So now, of course, families don't explain the whole world. They're just the bottom layer of the whole world. So now, if you want to look at the graph even more, one thing to use is the number of edges currently that go in between. So this is kind of a smaller fraction, right? This is a phi log n fraction. So if you want to understand this graph even more, one thing we could do is, okay, we understand families. Let's contract all the families, right? And let's look at the graph again. Once we contract all the families, the number of edges that remain is exactly the cross-cluster edges, right? Which is a phi log n fraction of the edges. So now we significantly reduce the number of edges in the graph, but there's still non-trivial edges floating around that have a lot of structure. And we don't know much about the structure of this graph, so what we do, we apply expanded decomposition again, right? We contract, apply again an expanded decomposition, and now what we get is larger clusters, right? Turns out that these nodes here are kind of nicely, these families are tightly connected to each other. So this will be one cluster, but these are separate clusters of families. And you can think of these as cities, right? There's like different people living together, might be families, might be people living together. Once you contract these households, then you get a bunch of households that cluster together, and this will probably be along city lines, right? Then, of course, what's the next thing you do? You contract all the cities. You get, again, an arbitrary graph. You do an expanded decomposition, and you get this might be now countries. You do this one more time. You get continents. You do this one more time, and it gets the whole world. Right? So very quickly, kind of, you get a nice hierarchical decomposition. And it turns out that this decomposition tells you everything that you need to know about the world in terms of flows, in terms of cuts, up to polylogarithmic approximation factors. So really, the whole world is just a bunch of families that are tightly connected into cities, that are tightly connected into countries, and up to a polylog factor and approximation. This is capturing, it's just a tree. It's a nice hierarchical decomposition which captures all the flows and all the cuts. Good. So that's kind of a very useful kind of cool thing. Let's see how we're doing on time. So now the one thing that, perfect, good. The one thing that expanders are not so great, it's actually, given that we have time, let me...
Sorry, quick question. In this analogy, the edges you're removing are like within the tag clusters to make them sparser?
No. No. So okay. So the first edges that you remove are the edges that intuitively go between families.
Right.
So those you remove, and then
There
what
shouldn't be
remains
that-
are families.
Right, okay. But there shouldn't be that many edges of those edges anyway.
Exactly. So there is only, let's say you set phi to
Okay, sure.
1 over log squared. There's only 1 over log and fraction of those. Okay. So now most of the edges are between families. If you just find your families to be at least 1 over log squared expanders. Right? But in some sense, you're interested in the structure of these edges, right? Of the edges that are not in families. In families that tightly connect the families, you know pretty well. I mean, they make families kind of really awesome places to be. You can route, you can randomly mix, you can do all kinds of things, right? But you're kind of interested in what's the structure beyond the families. So then what you do is you contract the families. And then if you look at the contracted graph, all the edges that are in the families are now basically this inner node, in a contracted node. So they kind of just disappeared. And the only edges that remain were the ones that you thought of as deleted, right? So instead of deleting, contract the nodes that you didn't delete. And now only the edges, only the CC edges, these cut edges, are the ones that are remaining. And that's your kind of next level graph, right? And you're hoping that that's in some points, those are all the connections that are not captured by families. And now you're looking for structure in those edges, and that will give you cities.
So you're contracting to connect to components, or like how?
Yeah, you could. Well, so you do one expanded decomposition, you delete the edges, and now you get a union of all the connected components are phi expanders.
Yeah.
Right. So you take these connected components, and those are the things that you contract.
Okay, got it.
Yeah, and there's different variations of this to actually contract or to do something slightly better than contraction. I mean, one is expander hierarchies, one is more RST. If but on a high level, this is I think on a high level you really should think of contractions.
Sure.
Yeah. Make sense?
Yeah.
Awesome. Sweet. Cool. Good. So yeah, let me just give you kind of one quick kind of. So if you think of routing or cuts or kind of even oblivious routing in networks, expander decompositions are kind of give you the right kind of structure. So in an expander, we know how to route. In expander, there's many different passes. In fact, you can use random walks to basically find a path between any two nodes. And you can even, because it's a random walk, how you route is independent of kind of what other demands are there. You're just finding a random walk that starts and ends at A. And that's nice, and we call that oblivious, because how I select my route randomly is independent of the rest of the demand, or oblivious from the rest of the demand. But if you do this in a graph that's not an expander, then that's less trivial, right? In particular, kind of on a high level, what should happen is if there's a tightly knit set of nodes, family, and you want to send between family members, you should probably stay within the family, right? You should not communicate that message to someone outside of your family and then again back into the family, because there's very few edges. There's a sparse cut to the outside. And if too many edges that should go between family members go over the sparse cut, you're going to over-congest those. So, and basically, if you just follow that high-level intuition that I should stay as closely in my social circle to communicate message as possible, then this will actually give you oblivious routings for arbitrary graphs based on these hierarchical expanded decompositions. Yeah. So in particular, what you do, so we do this, we find our families expanders, right? Then we contract those and we find these cities. And so if you write this down, then this gives you kind of a tree graph structure until we've contracted everything into the whole world. And then you can think of going the opposite way around and contracting in the same order, and this gives you this tree. Right? And now if I want to send from here to here, then we always said, you should probably stay within your family. The family is an expander, so we know how to route in here. We just do like a random walk-based routing. That's great, and even obliviously. Good. What if we want to route from here to here? I don't know, from here to here? or from here to here. If we route from B to B here, we kind of need to leave our family, but this person is in the same city as us. Right? So it turns out the best way to route is you route from your point to a random family member, random routing, from this random family member to a random other person in the city, somewhere here. On the other side, you do the same thing. So this person routes to a random person in its family, and then also routes to this random other family member, this random other person in the same city. And then you stitch together those passes. That's oblivious, right? Because I literally didn't look who else wants to send. Turns out that this is like competitive oblivious route. And then, of course, these two need to go all the way to the top. Good. Now, when I say these are competitive oblivious routings, then I mean this will find us passes that go that minimize the that minimize the congestion, because this thing captures cuts and flows and congestion extremely well. Right? What it does not do is it doesn't really work for length. And this is kind of where I want to go into the new definition of hop-bounded expanders. So expanders are extremely powerful, and they work well for anything that's L infinity quantities, cuts, flows, L infinity optimizations. Anything that's cost, length, delays in communication, right? These things here might get really, really long, you'll see in a second. They have low congestion, but it completely ignores delay. And in practice, or just also in theory, sometimes L1, you want min-cost flows, you want shortest path distances, and maybe you want routings that are not just like, that are not just streaming and you want to minimize the congestion, but you actually care what is the delay. And then expanders kind of have, they're not designed to do that. The definition is purely, it doesn't talk about length. And that's something we would like to change. Okay. Questions at this point? Cliff? Awesome. Okay, cool. So for the rest of the talk, this is the definition I want you to have in mind, kind of. Expanders are very good routing structures, right? And now often this is when I say expanders don't talk about lengths, and people tell me this is not really true. And in some sense, it is not really true. It turns out you're saying that it can be routed with congestion 1 over phi. But as we said, these random walk, like we can think of routing random walk base, right? So it turns out that we can make these passes also with congestion 1 over phi and of length roughly 1 over phi. This is also true and possible, right? In fact, these random walk-based things will maybe get 1 over phi squared, but if one doesn't choose them slightly cleverer, passes of length 1 over phi are always possible. Like them expanders have a diameter of at most 1 over phi. Okay, good. However, this is not good enough. In fact, this is exactly kind of something that doesn't work. And you can see it already in this routing here, where every time we go one step up in the hierarchy, we reduce the number of edges by a phi log n factor, right? On the other hand, we need to route within the expander, and when we uncontract this node, we need to find a route within the expander. So every round of uncontractions increases the length of our passes by a 1 over phi, and we lose an extra log n on top of it, right? So now if you just think about what is the length guarantees that we get about the length of these passes in this hierarchical routing, every step up, we reduce the complexity by a phi log n, so log n factor worse than just phi, and we increase the pass length by 1 over phi, but also lose an extra log n factor on top of it. In the end, we get nothing, right? There's no length guarantees whatsoever that one gets out of this. And this is something that's very tricky. Okay. Now let's change this. Let's maybe so this is our old definition. We get some, basically, the phi is the congestion. Now we would like to talk about length, right? So here it's actually, so I call something a phi, and this is also, this is a pseudo definition, right? The real definition goes through sparse cuts, but it's an equivalent characterization, right, up to some lines. So here what we're gonna do is the following. I want expanders that go over, that talk about meaningfully shorter passes, right? So I call them, let's say, L lengths, or originally I called them H hop, but maybe, yeah, maybe I stick with this. This extends to general lengths, but initially I just did it for like unit length passes, and we're talking about hops. So an H hop phi expander is a graph that where any reasonable demand can be routed with congestion phi, and length something shorter, H, yeah. So like, yes, makes sense. Right? So now we're basically saying, instead of a length of 1 over phi, we want a shorter length, right? So I'm just saying we should be able to route over passes of length H. And this is basic, almost the definition of an H-hop expander. There's one thing that we need to fix here, right? Where before that, any reasonable demand, and still what means reasonable in this context here? Again, probably I shouldn't send or receive more than my degree. That stays the same. How should we change this? Within the same connected components, that better still be true, but also if I want to send only over passes of length H, then what should I replace this with? Is that the only restriction to make it reasonable?
Into the 1 over H or something? The degree, you mean?
No, the degree, you still should, you should only, if you have degree of 5, you should only send or receive 5 packets.
But you have to increase the degree, right? To get a small, okay, so sorry, what was the question?
So, yeah, so I'm claiming that if you want to route over passes of length H, then in order to stay reasonable, it should be the case that our demand that we're asking to route is close enough to even route over distance H. So, right, so instead of just saying they should be in the same connected component, but they might still be really far away, then asking for this to be routed over an H-long path is not reasonable. And so instead of within the same connected component, we just say reasonable demands, that's unit, and sender receiver are at most H hops.
But do you want to guarantee that all pairs are distance so much H, like in these expanders?
No. So what I say is that is any demands that you give me, right? So you say I want this one node to talk to this node to talk to this, and this node to talk to this.
Mm-hmm.
I want the overall congestion to be 1 over phi, right? That's the parameter phi. But also I want the passes to be shorter what they usually are. Maybe not just 1 over phi long, but I want them to be even shorter. I want them to be H long.
The definition, the expander satisfies the definition of a H-hop expander with respect to demands.
No, if for every demand.
Oh, for every demand.
For every demand that's reasonable, you can route.
The diameter has to be at most H then, right?
Well, okay, so either you can say the diameter is at most H, or you can do it a little bit more general. You can say that the pairs that you ask me to route.
Right, but you're saying for every pair.
For any reasonable demand.
But then if you're defining reasonable by only the demands that are H hops away.
Yes.
Then haven't you not changed the definition? Okay. So for all pairs that are H hops away, you want to be able to route them with the same congestion as before.
Yes, exactly.
Yeah, using a path that's.
And of course, if I don't restrict to saying that, I mean, if I'm asking you to route to pairs that are further away than H and say, please route them over an H or pass.
It's impossible.
That's just not reasonable, right?
But it's also impossible, right?
Yeah, it's impossible. Yeah, it's in the same way that if I ask you to route between two different connected components, that's just not reasonable. That's impossible, right? And so the definition is really more or less the same thing. It's just saying anything that's reasonable, you should be able to do with like small lengths and small congestion, right? So there's a small twist here that one needs to if we have two nodes that are exactly h far away, and I force you to route them over paths that's exactly h or not longer, then there's very little flexibility here. This doesn't, in the end, the math, everything doesn't really work out nicely. So so there's a small slack here. Let's say I'm allowing to route you over passes of roughly length h, log in factor more to factor of 2 more, something like this. Right? But so anything that's h-hop close, any demand that's reasonable, I want you to route over this. And then if h is larger than 1 over phi, then normal expanders already do this, right? So this is in particular like interesting for h much smaller than 1 over phi. Because otherwise it's literally just the same as an expander. Good. So this is, again, this is actually not the definition. The real definition goes through cuts. So there one can go through the whole machinery and say, what is a hop-bounded cut? What is a hop-bounded sparseness cut? An h-hop-bounded expander is something that doesn't have h-hop-bounded sparse cuts, and so on and so forth. But kind of those things are slightly less natural. With this equivalent, you should really think of h-hop expanders as basically doing the same thing as expanders, just over much shorter passes, but only restricted to nodes that are close by because, well, everything else is not reasonable. Okay, so now let me give you some examples that this is really doing something different and incomparable to normal expanders. In particular, for example, a line. I claim, so let's look at a line that's a really bad expander, normally. Let's look at it, how good of an h-hop expander is it? So I claim for an h-hop expander, the line, how large can the congestion be in the line when nodes can only send their degree, which is constant here, I guess, and only close by nodes can communicate? How large can the congestion get? H, right? So and this is actually a 1 over h expander. Right? Because the congestion cannot get larger than h, which is about as good of an expander as it can be, because once it gets larger than this, it just becomes a regular definition anymore. So in fact, the line is a perfect expander, a perfect kind of h-hop expander. Right? Similarly, it turns out that in a grid, kind of great h-hop expander, right? Very different from normal expanders. So a grid is a terrible normal expander. Right? Okay, now is everything a great h-hop expander? Hopefully not, and that's a boring definition. So what's one graph that's not an h-hop expander? What's the typical graph that's not an expander?
Complete graph? Complete graph is expanded.
Two complete graphs and one edge in between.
Yeah, 2 cliques with 1 edge in between, right? I mean, we need something that has a sparse cut. So this is not a great expander in the normal sense. I claim it's also a really bad h-hop expander, because still I can say every single point in here is supposed to send to somewhere in here. See, so that's a reasonable demand to ask for. Everything is close by, it's just a matching, right? However, routing this needs to go over this middle edge, the congestion is going to be bad.
And this is what I mean by h-hop cuts. Like this cut is bad for even when you look at the number of points that are cut by the h-hop now.
Yes, yeah. So the cut version of this is slightly less natural, and so I'll prefer to not talk too much about how cuts are exactly defined. But intuitively, I mean, the intuition carries over, and yeah. So here's kind of this is a bad h-hop expander. This, the path in between is much larger than h, right? Here, this is much larger than h. This is a great h-hop expander. Why? And intuitively, why? Because in every local neighborhood of h, this either looks like a path, which is a great expander, right? Or it looks like a lollipop with a very short stem, right? So this is a great h-hop expander. Good. This is supposed to be an hour or something like this. Okay. Yeah, perfect. Good. So this is a definition. It's a new definition. It talks meaningfully about length. Many of the intuitions, algorithms, all the machineries that we have developed for expander doesn't go over straightforwardly, but largely goes over straightforwardly. Like largely can be made to work on these type of expanders. And so in particular, let me give you kind of the HOP, the statement of the HOP expander decomposition, which is similar to what we had before. For every graph, every phi, and every h now, right? So this is the new part. So exists a cut such that if I remove the cut from G, then so such that this is an HOP of phi expander, right? So the amount of edges that I need to remove is this. Now, the number of edges, so fraction of edges that I need to remove is at most phi log n times pi log n fraction of all edges, right? And this is kind of important in the sense that the total number of edges that I delete is independent of phi. Independent of h, right? So the path length that I'm getting is much, much less than 1 over phi, right? But my desired path length does not go into the size of the cut.
Because the size of the cut affects the depth of the hierarchy.
Oh, so this is the application then, yeah. So you're already like 2 steps further. If we then use this expanded decomposition hierarchically, and for example in oblivious routing, then cool things happen. Yes.
But if the size of the cut depended on h, then you'd have like h in the like.
Yeah.
They would maybe
So
in that case it'd be
something is trivial, right? If this here was 1 over h, right, then it's trivial, because then I could literally just ask for normal expanded decomposition where the expansion is 1 over h, right? Then I get path length h, and I get congestion h instead of congestion 1 over phi, which is even better, right? So that's boring, right? But instead, it's really phi. So meaning that if you have a certain budget of edges that you want to delete, this will go into your congestion. See, it will not go into your length. You can choose your length arbitrarily short, right? Of course, it's not, nothing comes for free, like it's incomparable, right? Of course, now it also only applies to short, close by nodes, because, you know, this is not, this being an HOP expander, this is not talking about demands between the endpoint of the line anymore. So we are forbidden, because it's just not reasonable, right? But expanded decomposition is really just saying that you can make your length arbitrarily small. You can control the length independently from the congestion. It doesn't change how many edges you delete. Of course, it only allows you to talk about nodes that are close by, because everything else is meaningless. Right? And good. So this is really kind of
So to be clear, this HOP phi expander is an incomparable definition to a phi expander. Like,
yes, well, incomparable in the
H,
following sense. If you set h to be infinite, or if you send
it'd be log n, then it's just an normal expander should have diameter log n anyway, roughly.
well, the diameter log n over phi. Yeah. So if you set h to be 1 over phi, or log n over phi, I mean, right now we're not super precise about the log n's, then it's literally just the same definition.
Okay.
Then nothing, I mean, then everything is exactly the same. So,
But for smaller h, it's not stronger or weaker than
no, for it's stronger in the sense that it guarantees you drastically shorter lengths, right?
Right, but it's not giving you a good expansion. Does it have to also be a phi expander?
Yeah. So if you choose an HOP phi expander and you have a large h, it's just an expander. Right.
Right, but an HOP phi expander need not be a phi expander.
No, it's as we said here, for example, the line.
So yeah,
it's really bad expander, but it's great
is what you said is that a HOP phi expander for small h is incomparable to phi expanders.
Yes,
okay.
And the reason why it's incomparable, so it's stronger and weaker, so incomparable. So in what sense is it stronger? It's stronger because it gives you strictly smaller path lengths, right? And it's weaker in the sense that it only gives you short path lengths for nodes that are close by. in some sense, because everything else, I mean, you can't have short path lengths for things that are far away, right? So that's just not reasonable. But this is the part where we restrict our demands to those that are short. That's what makes it weaker in some sense, right? The normal expanders don't talk about lengths of like, there's no restriction on the length. So any two nodes that are anywhere, you must be able to like connect with each other. And so this is why they're incomparable. Yeah.
So you could have some demands which are all farther than h apart in an h of phi expander for which there's no
guarantee.
Phi,
yes.
Even
Yeah.
any length. Okay.
Yeah. So like here, the demands that
Yeah,
if
good.
you want to send the first half of the line, wants to send to the second
Sure.
half of the line,
Oh, good.
right?
Oh, good. Yeah.
If you're saying, if you have an h that's much smaller than n, then you're saying, I want to talk about nodes that are, these are not things that are allowed.
Yeah, you
right?
can end congestion, but
And this would have in congestion, but this is a demand that we simply don't allow.
Good.
Because we're asking for short passes, then you shouldn't ask about routing nodes that are far away, right? And this is what makes this a bad expander. And if you once you forbid this and say, I'm actually only care about nodes that are close by to be able to communicate, then you're restricting yourself. But on the other hand, you can get the best possible guarantees almost, right? In the sense that now things that are close by actually get to communicate over passes that are constant competitive even to the actual distance. Yeah, good. And yeah, so I think the very last thing that I want to show is basically something that you already anticipated and did in your head. One cool thing that, so what happens if you use this hierarchically and for routing, for example? Maybe I'll do it here. And yeah, slowly for everyone who doesn't think quite as fast as Raj does.
Well, you gave me an idea yesterday, so I had a bit of time to think about this.
Yeah, I mean, I was trying to prep it in the talk, but yeah. So here, so now let's just do the same thing, right? So I do an H-up expander decomposition. Now for some different H and a different phi. So let's say I know that the demand that I want to route is between close by nodes, right? And I have some maximum the delays that I want to tolerate and that I hope is possible, right? Length, delay, cost, or is kind of the same thing. So I say this is the maximum delays that I'm willing to tolerate. Clearly, two nodes that where even the shortest path, if this is the only thing that I want to route, if my delay is shorter, if it's on the other end of the world and I want a delay that's less than like 0.1 millisecond, like less than 10 milliseconds, that's not possible because speed of light is just not that far, right? So now I'm saying I'm only talking about nodes that are close by enough that it's even potentially possible to route them with short delay. Right? And then I want the delay that's competitive. Competitive is, the speed of light or the shortest connection, ignoring congestion at all, right? And this is what I want to route. And now I do the same thing. I look at my network. I do an H-bounded expander decomposition. Anything that's larger than the delay, the 0.1 milliseconds that I'm willing to tolerate, that doesn't matter, right? I get some components of sorts. They're not really quite components because they don't disconnect, but I get local neighborhoods. I contract these local neighborhoods. In the local neighborhoods, we get kind of congestion that's small, right? Fine. And now here's the number of edges that we delete in this contraction, or is basically, again, a phi fraction. But when we uncontract them, exactly as you said, now we're not losing a 1/phi in length, but we're losing an h factor in length. And now what happens, and h is much smaller than 1/phi. So even if we bring this through the whole hierarchy, then think of, I don't know, just for concreteness of numbers, think of phi as 2 to the, like 1/2 to the square log n. In the contraction example, later on you can choose this polylog, but this is the easiest thing. Now, every time the number of edges reduces by 2 to the square log n factors, so the depth of this recursion, the depth, right, of our recursion in practice will probably be 5 or 6, but here this will be, like in theory land, so this will be squared log n, right? And now every time we lose a factor of h, and now we're just losing, usually we would lose a 1/, like a 2 to the square log n in length. I mean, we would have passes of 2 to the square log n times log n or something. to the power of the depth, right?
So this is why it's
Gives you
important.
nothing.
This is why it's always important for H to be less than 1/5.
Yes, I mean, once you go to normal expanders, this gives you literally nothing. This is just n. Once you replace this by h, where h is much, much smaller, you get h to the power of 5. H to the depth, so squared log n. In fact, in the end, one can actually just get something that's linear in h and a constant loss here, but that's goes way beyond this talk. So in the end, what one can get out of this is, if you tell me a fixed delay, then I can give you an oblivious routing that's constant competitive. That only works for nodes that have where this delay is even possible, but where the congestion is maybe polylog competitive, because even for the long lengths, it's polylog competitive, but that's competitive in the congestion compared to the best routing that works with this delay. Something that was kind of completely out of reach. In general, you can kind of see these things allow you to talk about lengths in a way that normal expanders don't. And there's one kind of nice new trick to this also, where whenever you talk about expanders, there's always going to be a loss of log n. That's just inherent in expanders. But even if you talk about flows and cuts, it's a constant expansion. There's still kind of the congestion is going to be log n. Passes are going to be log n. And with h-hop expanders, in the most extreme instantiation, you can set h to be a constant, and it still retains meaningful. And so this actually allows you to get constant approximations for multi-commodity flows, constant approximation for all kinds of distance problems, where if you were to normally apply expanders, there's just no way to go below polylogs. I think this is more or less kind of was a good intro, and we have 5 minutes left. So this is everything that I wanted to show. Very brief intro. Basically, just by going, this is flow-based definition of expanders. This is the one that extends nicely, and one can kind of add lengths to it, and then start doing all the kind of important work that we've done with expanders, expanded decomposition, hierarchical decomposition, algorithms based on it, but suddenly start also controlling for lengths, costs, and L1 quantities. Cool, good. Questions? Thank you, Kuba. Good, no questions then.
Longer questions probably, but not for the next 3 minutes.
Not for the next 3 minutes, yes. Actually, you said we have to leave the room in like 4 minutes, right? Yeah.
Actually, what is so you didn't say anything about how you compute these for the decomposition.
Oh, so the way that you compute these is similar to the ways that you do expand. I mean, all the algorithms and things that we've developed for normal expanded decompositions carry over here fairly nicely. So how do you usually compute an normal expanded decomposition? You find an approximate sparseness cut, you cut it. Find approximate sparseness cut, you cut it. If you want it to be really fast, then you need to make sure that the cuts that you find are not too small, because then it's very sequential.
Is there a way of are there scalable ways of doing this? Can you do this in NPC?
NPC,
you find these sparseness?
I don't know. So the algorithms that I know, you can do it in like log depths.
Okay.
Log depths, maybe log squared.
Sure.
I'm not sure, but yeah. So then exactly this point where you want to keep cutting sparse cuts, but you want the sparse cuts to be roughly balanced, right? Because otherwise you're sequentially cutting lots of small cuts and shipping it away, right? So there's a whole algorithmic tool set that's been developed over the last 5 years, really intensely. With lots of powerful papers, and in some sense, very similar things happen here. So you define an h-hop sparseness cut. You find one, you cut it. You find it, you cut it. If you want it to be very scalable and not sequential, then you need to be a little bit more clever and find roughly balanced sparse hop-bonded cuts, and you keep cutting those. And a lot of the work is basically trying to understand what is the right way to look at these, and once you found the right way to look at these, then it extends fairly nicely. If but you know, if you don't know what's the right way to talk and think and look about these, then a priori it's not, it's less clear. And so this is mostly what I've been spending a decent bit of time. Thanks for sticking around. Thank you, guys.